of vectors and properties of vector space. We will discuss the some new properties of physical vector space, namely what mean a distance and angle in the abstract vector space. But first of all, I recall some definition and proposition from previous lectures, and first 10 minutes we will be a subset of V. One says that U is a vector subspace of V if the restrictions of operations of addition and scalar multiplication by scalar to U equip U with structure of vector space R. Some simple example: if we have geometrical three-dimensional vector space, and let we have some basis in this vector space, and maybe some coordinate system, and let V be this physical vector space, three-dimensional vector space, and we can identify this vector space with arithmetical vector space R up 3 with elements. The elements of which is triples of real numbers. And let's consider the following subspace: U is coordinates x1, x2, x3 such that x3 is equal 0. And geometrically, this subspace is a vector plane, namely the set of vectors with certain coordinates is equal 0. and I can identify this subspace with arithmetical two-dimensional vector space R up 2. And maybe most simple example and other example. Let's consider the set W, the subset of V, the sets of triples x1, x2, x3 such that x2 is equal x3 is equal 0, and in this case we can consider this subset as a set of vectors which parallel to x O x. O x1. And easy to see that we can identify the set W with vector space R1. It's a vector straight line. Vector straight line. And we have the following inclusions and bending. W is subset of U and subset of V. But if we consider maybe some triangles in the vector space, and this triangle is not vector subspace, simple some sets, and the natural equations when the subset is the vector subspace. How to check that given subset is a vector subspace? On definition, the vector space is a sum set with operation of addition and scalar multiplication, and these operations are defined by some axioms, by some properties, and in correspondence of this definition we must to check these axioms. But easy to see that some of these axioms is not need to be checked because, for example, the axiom of associativity is fulfilled for all vectors in this vector space, and from this easy to follows that this axiom is fulfilled for some given vector in this subsets, and we can assert that the axiom of commutativity, distributivity also must be fulfilled for vectors from our subset. We need to check only zero axiom. What means zero axiom? This axiom asserts that on vector space is defined the operation of addition scalar multiplication. It's not evident that this axiom is defined, this operation are defined on given subset. Is not evident, and it can be false that this operation is defined. What means the operation is defined? If we pick some vectors from let's V be a vector space and X some subset of V. Subset. And we can we want to check that the operation of addition is defined on this subset. What mean the operation is defined on subset? If we pick some vectors from this subset and apply to these vectors operation addition, we obtain some vectors u plus v, and these vectors it belongs to the vector space, but we can to check that these vectors belong to some to our subset X, and if this condition is fulfilled for all vectors which belongs to X, we can say that the operation of addition is defined on X. Namely, for all vectors u v from v from X, maybe if u v belongs X, it follows that some of its vectors also belongs to X. And if this condition is fulfilled, we can say that the operation of addition is defined on subset X. And also, what mean the operation of scalar multiplication is defined on X? Also, if we pick arbitrary scalar lambda and every vector v from X, lambda v also must belongs to X. In this case, we say that the operation of scalar multiplication is defined on X. And if both operations is defined, both operations are defined on X, in this case, we say that X is a vector space, because from this condition easy to see deduce this all axioms. For example, the axiom 3 of vector space asserts that exists the element 0 vector such that 0 plus v is equal v plus 0 is equal v for all vectors v. For all vectors v. Let's prove that 0 in this case lies in X. Let's let V some vectors from X, and we suggest that X closed under this operation, and the second conditions, closeness under scalar multiplication operation, is fulfilled. And let V belongs X. Pick the zero number from R and multiply 0 on V. In this case, we get 0 vectors, and from this condition is follows that these vectors belongs X, and we check this axiom. Is this example of reasons for the conditions which define the notion of vector space. More precisely, we can formulate some strict proposition theorem. Let W be a non-empty subset of the vector space V. The following conditions are equivalent. First, W is a vector subspace of V. Second, W is closed with respect to the sum, to the vector sum and the product by scalar. Namely, U plus V belongs W for all V from W lambda V belongs W for all V from W and any real number lambda. The proof is enough evident if from item 1 is evidently follows item 2. If W is a vector space, on vector space is defined this operation and enough evident. If point 2 is fulfilled, we can prove that W is a vector space. This condition is a zero axiom, the zero axiom, and as I try to show that the zero axiom in this case is sufficient condition for that W is a vector space. We easy to check that other axioms are fulfilled in this case. More precisely, I suggest to accurately to prove that this all axiom is fulfilled and can be deduced from zero axiom in the case when W is some subset of V and these conditions are fulfilled. Let's to solve some simple exercise and check that some subsets is subspace of vector space. Example of exercise. Let W1 is the subset of R2 such that x minus 3y is equal to 0. Is this subspace? Let's consider such a subset. Let's try to check that these two conditions. First, let U, U1, U2, and V1, V2 be the vectors from W1. What means that U belongs W1? It means that U minus 3, U1 minus 3 U2 is equal 0. And such condition also fulfilled also is fulfilled from second vectors, and we have that some condition is fulfilled from vector v. And we want to check that u plus v is 0 as belongs w1. U plus v, the vectors with coordinates u plus u1 plus v1 and u2 plus v2. And we want to check this condition for both coordinates u plus u1 plus v1, u2 plus v2. And easy to see that u1 plus v1 minus 3 u2 plus v2 is equal and we can use the axiom of vector space, namely the axiom of commutativity and associativity, and rewrite this expression in this following form. And we can use this condition and obtain that this sum is equal 0. And we see that this set is closed with respect to the operation of vector addition. And also we can to check that this set is closed with respect to scalar multiplication operation. Let u is arbitrary vector from W, and lambda is arbitrary real number. And let consider scalar product lambda u, and we obtain a vector with coordinates lambda u1, lambda u2. And let's check the conditions which defined the set of W1. Easy to see that this difference is equal using the distributivity property. We obtain that this expression is equal 0, and it means that this set is closed with respect to scalar multiplication operation. And using this theorem, we obtain that this set is a vector subspace. And answer W1 vector subspace. Vector subspace. You can illustrate some draw the vector space V in this example. We can identify with physical three-dimensional vector space, and this subspace some plane in this vector space, and this plane is orthogonal the vector with coordinates this subspace is this plane, two-dimensional vector space is plane, and this subspace is straight line which pass through 0, and this straight line is orthogonal vector with coordinates 1 minus 3. And easy to see that all vectors which belongs to these sets, the vector which parallel to this straight line, the vectors with coordinates 3, 1. This parallel vector with coordinates 3, 1, and any such vectors, if you consider any such vectors which parallel this straight line, this sum is also have these properties. The sum of such vectors, the vectors which also parallel to the straight line, and scalar multiplication of any such vectors for any real number is also parallel to the straight line. And enough evident that this subset is vector subspace. But we checked these properties formally using algebraic calculation and theorem, which is criterion for that some subset is a vector subspace. Because in other many complex situations we can't to see geometrically that some subspace is some subset is a vector subspace. In this case, we can to check enough easier this properties, but this property, but in other more complex cases, it can be more complex problem. Okay, and the following theme of our lecture is a scalar or dot product in vector space. In our physical vector space, we can to measure distances between points of our physical space, and we can to measure angles between straight lines and between vectors. And our claim to define these notions of distance and angle in the abstract vector space. We have axiom which define the algebraic operation addition, scalar multiplication, but from this axiom not follows that we can also to measure distances or angles. And the opportunity of such measurements is complementary algebraic structures. And we will try to understand and define, to understand how to define this algebraic, these new notions. I call how to define the distance between 2 points in geometrical space. In the case of plane geometry, if we have 2 points A and B, and we can to calculate the distance between these points. Let A has coordinates x1 and y1, and B has coordinates x2 and y2. And we can consider a vector AB, and easy to see that these vectors has coordinates x2 minus x1, y2 minus y1. And let see the points of intersection of straight line. One of them pass through point R parallel, coordinate x, first coordinate x, and let also consider the straight line which passes through point B parallel to coordinate x, and let point of intersections of this straight line the point is the point C. And let's consider straight triangle ACB with right angle C, and we can to use the Pythagorean theorem and calculate the length of hypotenuse AB in this right triangle ACB, and length of hypotenuse is just the distance between point A and B and the length of vector AB. And Pythagorean theorem asserts that square of length AB is equal sum of squares of length AC and BC. And we obtain this expression. And the distance between point A and B is equal root square from sum of squares differences between corresponding coordinates of point A and B. And we obtain some formula for distance between points in geometric plane. And also to obtain the same formula for distances between points in three-dimensional vector space. Let A and B, some points in three-dimensional vector space, and let the coordinates of A x1, y1, z1, and from B x2, y2, and z2. And we also want to calculate these distances. Easy to see that square of these distances using the Pythagorean theorem is equal the sum of squares of legs in the triangle ABC, where C is projection of point B onto plane coordinate plane x0, y, and the legs C is a right angle, and we have that distance square AB is equal sum of squares AC plus BC. But AC, the distances between points A and C I'm sorry. I'm sorry. I'm sorry. I'm sorry. Let A, B, and I'm sorry. We need this some plane which pass from E and parallel coordinate plane x, y, z, and let A prime is projection of A onto coordinate plane, and C prime is projection of a point of C on coordinate plane, and A prime C prime is projection of AC. And this formula is true, but in this formula the distance AC is equal distance A prime C prime, because A prime C prime is projection of segment AC onto coordinate plane, and these segments lie in parallel plane, and because the vectors A prime C prime is equal vectors AC, and because the lengths of these vectors are equals, and the square of distance AC and square of distance A prime C prime is equal, and it follows from previous reasoning, is equal the sum of squares of differences between corresponding coordinates, namely x2 minus x1 square plus y2 minus y1 square. And BC, the vector BC has the coordinates z2 minus z1. And substitute this expression in this formula, we obtain that AB square is equal the sum of squares of differences between corresponding coordinates. We can suggest that this formula can be true for arbitrary vector space, and we'll try to define distance between 2 points in the abstract vector space by the following formula. Let Rn be arithmetical vector space and U some vectors in this vector space, and this vector has coordinate u1, un. Let's define the lengths of these vectors by the following formula. We can generalize this observation, and we can introduce some new notions of length or norm of arbitrary vector in the abstract vector space. What means this notation? This some abstract new object, and we will define the norm or length of vectors by some properties. We want to generalize some properties of length of vector, which defines by this formula. We no need to suggest that the length or norm is defined exactly this formula. We will use only some properties of this formula. That we can formulate some property. First of all, let's prove some properties for the legs which defined by exactly this formula, and let's formulate these properties for the distance which defined exactly define this formula star, which use notation star for this formula. We have the following theorem. If V, the vector in Rn, and lambda some scalar, then the length of phi greater or equal 0. Distance is non-negative. Second, the length of vector v, or distance between 2 points in space, is 0 if and only if v is equal to 0. Only the 0 vector of length 0. Only the 0 vector. Only 0 vector has the 0 length. The scalar product of lambda and v, if we consider the length of scalar product lambda and v, the length of this vector is equal product of model lambda and length of v. We use the proof is if enough evident. Proof v is equal square root from sum of squares of coordinates of these vectors, and sum of square is non-negative, and root from non-negative square root from non-negative number is also non-negative. We consider arithmetical square root. If such sum is equal 0, we easy to deduce that all coordinates also are equal to 0. And last item of this assertion, lambda v is equal sum root square from sum of squares and this theorem is proved. This theorem is proved. We will use these properties and define the abstract distance abstract abstract notion of distance in arbitrary vector space. Precisely, let V be an abstract vector space. We will say that in V is defined the norm of vector or distance if V be a vector space, and we will say that define the norm or distance if is defined some mapping from V in real number field R, and this mapping is defined by the following properties. V is non-negative for all V as V. Second, the norm V is equal 0 if and only if V is 0, and third property, the norm of lambda V is equal lambda multiply V. We also to use the notion of norm using two straight bracket, and use for norm the following notation. We want to use various notation for norm of number lambda. In this case, norm is absolute values, and the norm of vectors. In this case, the norm is norm of vectors. But this notion, norm of real number and norm of vectors, is the partial case of some general notion of norm. Absolute value of numbers is partial case of norm of vector, and we can also the same notation for all this of both of this notion constructions. And we also define distances between 2 points A and B as a norm of vector AB, or using second notation is the norm of vector with endpoints A and B. And we define the notion of distance in abstract vector space. But how to define the angle between two vectors? The angle between two vectors and the angle of triangle. easy to see. If we have two straight line and angle in this straight line, we can define as an angle between some vectors which parallel to this straight line. In the straight line we have the two straight line are defined if this straight line are non-parallel and has some point of intersection. These two straight lines are defined. These two straight lines define four angles, but to various angles, two pairs of vertical angles, and each pair of vertical angles have the same measure. But in the case of vectors, the angle between vectors is is defined uniquely. And how to define the angle? How to define the angle? And for the definition of the angle, we need originally to define some notion of dot or scalar product in geometrical space. How we define the abstract distance? First of all, we consider the notion of distance in geometrical vector space and consider the some basic main properties of this concrete notion of distance, and after them we use these properties to define the abstract notion of distance. And we'll follow this way and repeat this construction in the case of angle. First of all, we formulate some main properties of angle in physical space, and after them we generalize these properties and define the abstract notion of angle in abstract vector space. And let's start from geometrical vector space in geometrical plane, and consider two vectors A and B, and let's define the notion of dot or scalar product. Dot or scalar product. Definition. If U and V are non-zero, vectors in plane or space, maybe in arithmetical two-dimensional space or arithmetical three-dimensional space. Then the scalar or dot product of u and v denoted u point v or uv in bracket is defined as product of lengths of this vector on cosine of the angle between this vector. What mean exactly? Let's note that product of length of vector v on cosine theta is exactly equal the projection of this vector on vector u. And the scalar product is exactly product of projection of length of vector is product of lengths of vector v on projection of vector v on vector u. If use notation v and u as v на cosine theta, we can rewrite this definition in the form of product length of vector v on projection vector v on u. This is definition of scalar or dot product. We can rewrite this definition in the coordinate form, but for this we need in some properties of this scalar product. Proposition. Easy to see that the scalar product is commutative. The product of vector u and v is equal scalar product v and u. Easy to see. If we change the order of vector in the scalar product, the scalar product is will the same after transposition of the after the transposition of the vectors u and v. And second property, if we multiply vector v on sum of two vectors v and w, we have the distributivity property. Third property, the scalar product is equal of square of length of vector v and greater or equal 0. And scalar product is equal 0 if and only if u is equal 0. Easy to see that the important third property, we can see that scalar product is exactly the square of length of vector u and exactly the square of distance which is defined by vector u. The first property is evident, and second property. The second property is also enough evident. Let's consider vector u and to vector v and w. And easy to see the projection of sum v and w on vector u is equal to the sum of projection. And from this enough evident property, easy to deduce property 2. Actually, the product VW is equal product of legs of vector u on projection u, v and w, and is equal u projection v projection u w. And using the distributivity property for numbers, we obtain the property 2. And we obtain some property, and we can use this property to define the abstract dot product in abstract vector space using this property. We also we also can to get some exact definition of scalar or dot product in arithmetical vector space. We identify abstract vector space with geometrical vector spaces using some special bases in geometrical space. In the case of vector plane, we can consider some orthogonal vectors I and j, and the scalar product of these vectors is equal to 0 because these vectors are orthogonal, and this scalar product is product of this length or cosine of right angle, which is equal to 0. After them, we easy to check that scalar product of abstract scalar product of vectors in the geometrical vector space with this basis is equal using these properties. We easier to see that is equal 0, is equal 0, this is equal 1, this is equal 1, and we obtain this formula for scalar product. And we can generalize this formula for scalar product in abstract arithmetical vector space Rn. If we have abstract vector x and y, and we can define scalar product by the such formulas. And we can see that if square of x vector is equal scalar square, and we obtain that these two definitions of distance between 2 points of length of the vector is concise, are concise. Okay, my time is over and I'm finished.